Greetings, Dr. Dan with Optimal Optics here to introduce Unit 6 Prisms. Prisms are famous. They've been celebrated in song. Johnny Cash sang about the Folsom Prism Blues. That was a joke. So the definition of a prism is two refractive plane surfaces inclined toward each other at a refracting angle, and we call that angle beta. So I have two prisms shown here. Prism on the left is face front. Prism on the right is edgewise. And there's angle beta in the prism on the right. And we'll squeeze in angle beta over there in the prism on the left. Now, the thickest part of the prism is called the base, and the base does not have to be at the bottom. You can put your base wherever you please, any direction. It's always the thickest part of the prism, though, and the apex is the thinnest part of the prism. In our edgewise prism, the apex is on the top and the base is on the bottom. Now, the imaginary line that connects the base to the apex in a prism is very logically called the base-apex line. Someone probably stayed up all night thinking about what to call it and came up with this name. And it makes a 90-degree angle with the edges that it comes into contact with. Now, let's send a light ray into the prism on the right. We'll construct our normal. The ray of light will pass from a material of lower index, air, into the higher index material of the prism, and it will be bent toward the normal. Now we'll construct a normal on the second face of the prism. And now the light ray is traveling from a higher index inside the prism to the lower index of air outside the prism, so it will be bent away from the normal. So a very important principle of prisms is that if a prism is surrounded by a material of a lower index, the light ray will always be bent toward the base. Now a thin prism is defined as having a refracting angle beta less than or equal to 15 degrees. So let's draw a thin prism. And we'll send in a light ray. Try that again. There we go. And the light ray will be bent toward the base as it exits the prism. Now, if the prism had not been there, that incident light ray would have continued along the dashed line. So that angle between where the ray would have gone without the prism and where the ray was refracted with the prism, that angle is called epsilon. Oh no, another Greek letter. So epsilon is defined as the deviation of a thin prism. And assuming that the prism material has an index of n and that the prism is surrounded by air, epsilon is equal to n minus 1 times beta. And both epsilon and beta are in degrees. Now, let's say there's an object at the beginning of this incident light ray. When you view the image from the right side of the prism, we'll put an eyeball there, it looks like the image is at the end of the refracted ray, we extend it back along the dashed line, and there's a virtual image there. So you see the image is moved toward the apex, another important prism concept. Images are moved toward the apex while the light ray is moved toward the base. So let's draw another thin prism. And let's draw a screen 1 meter away from the prism. We'll send in a ray of light perpendicular to the screen, and it is refracted toward the base. Now, if the prism had not been there, this dashed line is where the ray would have hit the screen. And the distance between that point on the screen and the point where the ray that has been refracted actually hits the screen, that distance is 1 centimeter on a screen 1 meter away. So in that set of circumstances, we say that this prism has a power of 1 prism diopter. 1 prism diopter shifts the ray of light 1 centimeter on a screen 1 meter away. So a 2 prism diopter prism would shift the light 2 centimeters, and so on. The conversion factor between degrees and prism diopters is 1 degree equals 1.745 prism diopters. So if you want epsilon in prism diopters, it would equal 1.745 times n minus 1 beta in degrees. So I hold in my hand a prism, 8 prism diopters. I'm going to hold it in front of the camera lens in different directions, and I want you to predict which way the image of the stool will appear to move. I'm going to be moving my stool sample. This could get a little messy. So I'm starting with the prism base down. Make your prediction. The suspense is amazing. It moves the stool up toward the apex. Now I'm going to hold the prism base up in front of the camera lens. Make your prediction. Moves the stool down toward the apex. Now I'm going to hold the prism base left in front of the camera lens. And it moves the stool to the right toward the apex. And I'll hold the prism base right in front of the camera lens, and the stool moves to the left toward the apex. Now I hold in my hands 2 prisms, each 3 prism diopters. I'm going to hold them against each other so that the bases are in the same direction, and I'm going to hold them base up. So what happens is the 2 prisms combined, they add up to 3 plus 3 equals 6 prism diopters, and because it's base up, the stool moves down. Now I'm going to rotate one of the prisms, so now one base will be up and the other base will be down. They're opposite to each other. And I want you to predict what the stool will do when I put this prism combination in front of the camera lens. Nothing happens. It's like looking through glass or plastic. And that's because now the prism powers subtract from each other. They cancel out. Now what I'm going to do is I'm going to hold one prism stable while I slowly rotate the other one. We're going to start with both bases up. So we have our 6 base up prism total. And I'm going to slowly rotate the prism in front. Let's see what happens to the stool. And you can see that the stool slowly moves in a circle. We continue until both bases are up again, and we're back where we started from. Now, let's draw out what we just saw in the video. I have 2 prisms drawn here with the base apex lines at angle gamma to each other. One prism we'll call P1, one prism we'll call P2. and gamma is the angle between their two base apex lines. Measured in degrees. Now, there's a formula for the resultant power of these two prisms. You can also calculate the power using vectors, and we'll do that in Unit 6P. But if you want to use a formula, the formula for the total power equals the square root of P1 squared plus P2 squared plus 2P1 P2 cosine gamma. Now, there's an angle of the resultant ray of where the image is formed. As you saw in the video, that chair moved in all sorts of different directions. So again, you can figure this with vectors. I'll show you in Unit 6P, but if you'd rather plug into a formula, this is it. So theta is defined as the angle with respect to the P1 base apex line, and the tangent of theta equals P2 times the sine of gamma divided by P1 plus P2 cosine gamma. Now remember that the power is maximum when the bases are aligned. In that previous video, when each of those three prism diopter prisms were against each other with the bases in the same direction, we had a total of 6 prism diopters. And remember, the power was minimum when we had the bases opposite to each other. So in the case of two prisms of the same power, you end up with a 0 power prism in that orientation. The powers are subtracted. So let's see if that works when we plug into the power formula. So let's say the power of the first prism is 3 prism diopters, the power of the second prism is 3 prism diopters, and the bases are toward each other, they're touching. So total power equals P1 squared, which is 3 squared, plus P2 squared, which is 3 squared, plus 2 times 3 times 3 times the cosine of 0 degrees. Recall from trigonometry, the cosine of 0 equals 1. So under the square root sign, we have 9 plus 9 plus 18, which is 36, and we get a power of 6 as expected. Now, let's place the prism so that the bases are opposite to each other. When that's the case, angle gamma equals 180 degrees, and if you recall your trigonometry, the cosine of 180 degrees equals -1. So now we're going to subtract the last term under the square root sign. So we have the square root of 3 squared, which is 9, plus 3 squared, which is 9, and then minus 2 times 3 times 3, which means we end up with 18 minus 18, and we have a power of 0.